Hi everybody, this is Dan and I'm going to do a video tutorial today on how to design a gearbox. So there will be a little bit of CAD. It's not going to be completely SolidWorks today. It's going to be mostly figuring out what parts to use, where to get them, and how to come up with the basic design. So let's talk about designing a drivetrain gearbox, for example. The place to start would be to go to motors.vex.com. They have a really nice chart for all legal FRC motors. The motors down here are generally for mechanisms, and up here are the bigger motors, more power for drivetrains. So the Falcon's a great motor, but they're out of stock. We can't get our hands on those, so we can't really use that. We do have a lot of sim motors in stock. They're pretty cheap, and they're ubiquitous. So let's talk about using a sim motor for a drivetrain. Now some of you might say, well, why don't we just stick a wheel on the end of the motor and hook it up? And I'll explain why that's not going to work. So what this is saying, the free RPM speed, means this motor spins at 5,300 RPM if there's nothing attached. So we're going to lose a little bit, maybe 10%, if you load it down with something, which we'll be doing because we'll be putting a robot on it. So let's multiply that out. And so our real RPM is going to be around 4,800. And if we divide that by 60, then that's saying that's about, RPM is revolutions per minute, so that's about 80 revolutions a second. So if we were to put a 6-inch wheel, let's find their circumference by multiplying times pi. That's an 18-point-inch revolution. So every time a 6-inch wheel goes around, it moves about 18.8 inches. And if we talk about doing 80 revolutions a second, then that's 1,500 inches per second that wheel will move. And if we divide that out by 12, then that's saying that our motor and our wheel attached directly to it will move about 125 feet per second. Some of you might say, that's awesome, that's super fast, that's exactly what we want to do. The problem with this is there's a direct relationship between torque and motor RPM. The faster the motor goes, the less torque you'll have. So if you don't give it any gear ratio, you'll have very, very little torque. So for something like a shooter where you're just going to insert a ball and make the ball shoot, that's great. But when you're talking about a drivetrain, you need to push against other teams or you're pushing a heavy robot around, it's likely that hooking that wheel up, the motor won't even have the torque to be able to turn. It'll heat up, overheat, and burn up. So it's simply not going to work. So we need to gear that down. And you might say, well, I have no idea what a good ratio would be or what a good speed would be. Generally for FRC, anywhere from 10 to 18 feet per second is good. So let's say we wanted to go 15 feet per second. That means our gear ratio will be right around 8.3. And you're never going to get exactly 8.3773. That's not realistic. There's no set of gears that you're going to find that'll do that. So what we'll do is let's figure out where we can find a gear ratio where for every output rotation one time, the motor will spin 8.3 times. So you need a little gear on the motor and a big gear on your output shaft. So let's figure out where we can do that. Okay, so let's see if we can find ourselves some gears. So if you go to VexPro again, and we go to gears, let's find a motor pinion first. So here are your motor pinions, 20-degree pressure angle. Okay, and you can see they have different pinions for different motors. We need a sim pinion, and they have different sizes. So what size should you use? Well, the smaller the pinion you use, the smaller the output gear you use. Smaller the output gear, the lighter. So, and the smaller the gearbox dimensions overall. So what we want to do is pick the smallest one we can that'll work for us. It's also a little bit cheaper, you'll notice, and when you're doing a bunch of gearboxes, that can add up. So let's pick the 9-tooth spur gear, and then you say, okay, well, if we have 9 teeth and we know our gear ratio is 8.3, what should our output gear be? And so we need a 74.7 output gear. So let's go back up and look at the output gears they sell. If we scroll down, they do sell a 72 and a 74 gear. Now 72 is a much more common gear that we use in other places, so for that reason I would probably pick a 72. You'll go a little bit faster, but it's nice to use common parts, and if we have some in stock, then we can reuse them. So we'll be looking at a 70-tooth aluminum gear and a 9-tooth motor pinion. So 72 divided by 9. So this will give us an overall gear ratio of 8, which is a nice round even number, so that works well. Okay, so we've selected our parts. Now, the great thing about VexPro is that they provide their CAD files at the bottom of the site. So if you want a 72 tooth gear, all you have to do is find it and hit download. Now these are going to download in a format called step, and that's something that we don't typically use in SolidWorks, but we can import it pretty easily. So let's grab our motor pinion as well. Again, that was a 9-tooth spur gear. So if you scroll to the bottom and you find CAD files, you'll find not Falcon, not 775, not bag, there's the sim motor. So we're looking for a 9-tooth spur gear. That one right there. Let's grab that. So let's fire up SolidWorks and import these two gears and save them and apply materials to them. Okay, so let's open. Okay, and we apply steel to that since it's a steel gear. And then let's open our 72-tooth spur gear here. Now the spur gear is actually 7075 aluminum. It's a different material. And then we'll save that as well. So now we have our two gears and we're ready to build our gearbox, or at least start on our gearbox. Okay, so let's make a new part. And the first part we're going to make is a plate to hold our motor and our bearings to that. So and right now you just kind of need to know the dimensions of what you want to build. So if you go back to your gear, you can see how big under drawing your gears are. So if we look at a 72 tooth gear, the outer diameter will be 3.7 inches. So this will actually have to be 4. Otherwise the gear will stick out the top and the bottom. And then how thick should you make your plate? Well, we have 1/8 inch, 3/16, and quarter. Quarter is pretty heavy duty, but you can pocket it. You can take a lot out of that. Let's do that. Let's make it a 1/4 inch. And then we'll make that material aluminum as well. So let me add aluminum. May as well make it a favorite too. 6061. Okay, so there's our aluminum plate. Now, what we need is a hole for the motor, and then we need a hole for the output shaft as well. So what I'm going to do is I'm going to draw a center line because we'll put both holes right in the middle. Okay, so here's the hole for the motor. And then if we go back to VexPro and we look for the sim motor, it'll give us dimensions on how the motor mounts. So if we look at a sim motor, down at the bottom there'll be a drawing, and we can see the mounting holes. So the mounting holes are 2 holes. They're on a 2-inch around circle, and they're a 0.159 diameter hole. So, and then this hole in the middle is a 3/4 inch. So to give it some room, I'm going to make this 1 inch. That'll make the motor shaft fit through. And then what I'm going to do is draw a circle right here. See how that little line shows up? That means you're vertical with it. And I'm going to say 0.16. And then this needs to be 1 inch away. It's a 2-inch diameter radius, so that should be 1 inch away. Now let's move this motor, give it a dimension from there to there, and make it 1.5 inches. Perfect. Alright, so what we're going to do is we're going to mirror this hole there across there. There we go. And now we should be able to mount the motor to that. So let's save this as the motor mount plate. And then what we're going to do is we're going to do a new assembly, and we're going to take this brand new motor mount plate and we're going to put it there. So let's just do a quick test fit. So under assembly, let's insert component. Now if you go to our GrabCAD and you go to FRC common parts, you'll see we have a ton of parts that are already downloaded, and it's very likely we have a sim motor ready to go. There it is. So let's take this face of this motor and mount it to this face here, and then let's take this hole here, mount it to that hole there. Now that those are mated, it's around that circle, but we can still move things around that way. So we need to mount this other hole and mate this other hole to there. And now that we've done that, we've started our gearbox. Okay, so let's save that real quick. There we go. Okay, so we've got the motor on there. Now we've just got to get our other gears. Okay, so let's open this plate back up. And we know that we need to add another hole somewhere over here for our output shaft. You say, well, how big should that hole be? Well, whenever you have something spinning like this, you're going to want a bearing. And bearings are generally 1.125, an inch and an eighth. And we'll have to download the bearings. I think we have some in the common parts anyway. So now if we look, we have a second hole, and we can add a bearing there. The question is, what is the distance between that? And that's going to require a little bit of computation. It's not too hard. But your center to center on your gears is calculated using your data from your provider. So if we go back to VEX and we look at our motor pinion, this pitch diameter you'll see at the bottom under the drawing. So you've got your outer diameter, but when you want to mesh the gears, you want to worry about your pitch diameter. So let's find our 9-tooth sim gear. There it is. So we have a 0.5 pitch diameter, so it's a half an inch across. And so from the center to there would be a quarter of an inch. So that's pretty easy to remember. Now, let's find the pitch diameter of our other gear, which is a 72 tooth. So the 72 tooth has a pitch diameter, not an outer diameter, but a pitch diameter of 3.6. So from center to center would be 1.8. So we need to add those two up. So 1.8 is the center to the outside of the pitch diameter of the larger gear, and then we add a quarter of an inch to that for the spur gear. So we should have a center to center distance of 2.05. And then now the nice thing is, once you do this, if you do need to change your gear ratio, it's very easy to change your center to center distance. So 2.05. And there we go. So now, if we go back, we can insert a bearing, and when we put our gears in, they should be GrabCAD, common parts, bearings, like the VEX Pro. Now we're going to use a 1/2 inch hex. I'm going to use an output shaft that's hex, because hex is the best. Alright, so let's mate that face to that face, and then we're going to make these concentric right here, that and that. And what we have right there is the start of a gear box. So let's insert our 9-tooth spur gear. So that's what's going to go on our motor. So we'll mate that to that. And then what we have to do is we have to make ourselves an output shaft, so a 1/2 inch hex output shaft. So we're going to do a new part, right plane, there we go, made ourselves a nice hexagon, and a 1/2 inch hex is from there to there. And let's start with a 6 inch long shaft and make it out of aluminum. The nice thing is if you use the correct materials in all of your parts, then when you can actually use the SolidWorks program to tell you how much it will weigh. So let's call this the output shaft. So we're going to insert that new output shaft we just made right there, and we're going to mate it onto our bearing. Now, because the bearing is concentrically mated in that hole, it will still rotate. It's not exactly how the bearing would rotate in real life, but you'll get the picture. Okay, now we're going to mate that face to that face just so they're flush. And I'll show you how we'll actually hold that in position a little bit later. Alright, so now we've got that. So in theory, if we've done our calculations properly, when we mount these two, they should mate properly. The two gears should be in alignment. There we go. And then what I'll do is I'll just get them close, and I'll show you a neat trick you can do with the gears that's kind of fun. Okay, so these gears look like they are pretty well meshed right there. So a mate you can do under mechanical is a gear mate. And so what you can do is you can say, now you got to do the circular part of the gear and the circular part of this gear. And then you need to give a ratio. Now we know we have a 9 tooth and a 72 tooth. There. So now, when we spin this, you'll see they actually mate properly. So now we've got a pretty good gearbox going. The only problem with this is these shafts are cantilevered, meaning there's no support on the other side. So there's nothing preventing this stuff from falling apart. So what we'll need to do is add a way to hold this all together. So what I'll do is I'll modify my drawing, and I'm going to make some spacer holes and some mounting holes. Okay. Generally, 1/4 inch bolts are a pretty common thing we use, so we'll make it a 1/4 of an inch. And then let's space them off from the top by 1/2 and 1/2. This is a little bit generous. You know, if we were doing a real gearbox where we were trying to save weight and things, we'd probably cut this all down. We'd definitely pocket this out. So let's mirror this one across here. Keep the symmetry. That's always a good way to handle things. And then we're just going to draw this for reference so we can mirror our mounting holes on the other side too. Now, you don't always get the luxury of being able to mirror things, but since this is a pretty simple gearbox, now we have 4 mounting holes that are pretty reasonable. So go back here. Okay, so this is looking pretty good. Now the issue we have is we've got to make a sandwich out of this. So we need a spacer to go from there, and then we need another plate on the other side. So let's open this plate up, and what we're going to do is we're going to say File, Save As. I'm going to say Save as a Copy and Open. And instead of the motor mount plate, this will be the outer gearbox plate. Now this is a completely different file. If you were to switch back and forth, you can't really tell, but this is up here the outer gearbox plate. And what I'll do is I will actually change something so we can see the difference. So I'm going to make this big enough that you can fit your wrench in there so that when you need to adjust it, now you can see the two plates are different. So what I'll do, this will allow us to remove the screws that hold the motor on, the bolts that hold the motor on, even though we have the output plate on. So a little design thing like that that's kind of handy. Now this obviously plate can move around anywhere, so how wide should this be? Well, we don't really want that motor pinion sticking out a bunch. We need it right about there. So how would we space this off? Well, there's this great website called McMaster Carr, and McMaster Carr has everything in the world that you could want. So if we go to McMaster Carr and we type spacers, we know we need them for a 1/4 inch bolt. So spacers and a number 1/4 inch bolt. There we go. Let's go with plastic. generally pretty cheaper. So now we have tons of spacers available. They're not super expensive. We just need to know the distance, the width of them. So I'm going to evaluate. We can hit the measure button and we can measure. I kind of roughed it in. So this is 0.73. So it looks like if we did a 0.75, that would work really well. So let's do that. The great thing about McMaster is if you find a part that you want, you can click on Product Details, and right there is a 3D SolidWorks save file. So we can save that, and then we can open it. And again, it's always a good idea to change the material. Now that, let's see if we can remember what that was. That an ABS? Nylon. Okay, we should have nylon as one of the plastics here. Let's see, where's nylon? There it is. Okay. And then if you want, you can also give it the appearance that the thing will have. Cool. So that's the spacer we have. Now what's really nice about this is that part number right there. If you were to grab that and put it into Google and search McMaster car, you would find that it would come right up. And so if you build something with McMaster parts, it's really, really easy to order them. The cool thing is a pack of 100 is $12. So these are pretty cheap spacers, and McMaster ships really, really quickly. So we could have this built tomorrow if we wanted, if we had the gears. So let's grab the threaded part here, and let's mate that face to that face. That's great. We got this. Got to move around. So let's make these concentric. So make that line up with that. Now this still moves around freely, so let's make that concentric with that. Now it still can move in and out, so we have to mate that to that face. Now our sandwich is mostly complete. This thing it can spin up and down, but it can't move in and out. So let's grab another spacer. Stick it right there, and we'll do the same thing. Mate that face to that face, concentric, concentric, and then I like to move it the other way just so you can actually see it mate properly and click into position. There we go. So now we have a gearbox, and of course, it'd be a good idea to add spacers in all four corners. So let's do that real quick. We go. Alright, so we have a gearbox. Now again, the problem with this is this shaft is unsupported. So what we'll do is let's just grab another bearing. That bearing there. And let's spin it around and put it in this side. Now you see that flange there? That thing means it can't come out the other side. That's why they have that flange, so it'll stick in there. So if you bolt this all together and the flanges are both on the inside, then the bearings cannot fall out. If it was the flange on the other side, you could see it could kind of slide right off the shaft that way, and that's not really what you want. Okay, so let's just line this up and mate that together. There we go. And then we want this lip, this flange, on the inside of that, like that. Okay. Now you can see we do have a little bit of space here where this is not moving. So what we would do is we're going to mate that face to that. And what would be required here would be a spacer to go from there to there. Let's just get a quick idea of how it's looking. Looks pretty good so far. And again, you can see those bolts. Now, the other good thing about McMaster is if you want to find a bolt, it's really easy to do. So happens that those are 1032. So if you were to look at your sim motor, and you go to the drawing, it should say, I know this from experience, it should say that it mounts with a 1032. Yep, so you know it's a 1032 and 3/8 of an inch deep. So we can go back to McMaster and we can find ourselves a nice 1032. And you know the plate's a quarter and it can only go 3/8 deeper, so let's call it a 1/2 an inch. And we'll grab a socket head and let's make it a 1/2 inch deep. Alloy steel is fine. Cheap, 100 for 10 bucks. So let's get that. Again, go into the product detail, scroll down, and there's your SolidWorks file. So let's open that McMaster thing we just downloaded. It's an easy way to get fasteners. You can create your own, but man, this is way, way easier. So sometimes McMaster leaves the sketches on, which if you see it in your drawing looks a little funky, so I like to just kind of hide those. And again, always a good idea. So that's material. Don't really have a steel alloy in there yet, so let's just do that for the moment. Okay, so let's insert that bolt. I like to give it a quick rotate just there. Now we know we want to make it concentric, so since the cap screw, it's nice and easy. It's got an easy head to do that with. Make it concentric with that top hole, and then pull it out. And we want to mount that face to that face. And there we go. So now we've got one screw in. Simple copy, paste. When you copy paste, don't just grab the item, grab it in the tree, and then hit Control C, Control V. Works a lot better. Alright, and then we're going to mate these to be concentric. Pull that out of there. There. Okay, so our motor is mounted. We know what screws we need to buy. We know what spacers we need to buy. We know what gears we need to buy. There's only one thing left we've got to do, and that is measure between this face and this face. So let's do that quickly. And so what we'll have to do is probably make a custom spacer out of Delrin. That will work. So that's 0.13. Well, that's only 5 thousandths off from an 1/8 inch spacer, which are available as a product. So be willing to bet if you go to our GrabCAD and the common parts and go to spacers, you will find a 1/2 inch round spacer that is an 1/8 of an inch thick. And there it is. So let's make this concentric with our bearing. And then you could either mate it to the gear or the bearing. I'm going to mate it to the gear. And that'll just give a little bit of difference between there and there. Okay. So if we look real closely, there should be a very, very small difference there. Perfect. But that is a very, very nice snug fit spacer that just happened to work perfectly. Alright, so now we have our plain gearbox. We have holes to mount it to. Now the one thing I would say, Forrest would agree with me, is what you always want to do is hit fillet, and then that, and that, and then let's call it an 1/8 of an inch. And let's preview that. What that does is it rounds the corners a little bit, and when you're either machining it or you're going to water jet it or laser cut it, first off it's less sharp, which is always a good thing, especially if you're doing it out of aluminum. The other thing that's really nice is it's stronger, so especially in corners, internal corners, you're going to want to do that. So you can do the same thing with this one. You're going to want to fillet the corners, and do it on internal and external if you can. Gives a little bit more of a finished look. Okay. Alright, so there's our gearbox. Now again, if we want to go over to McMaster Car, you can find yourself a nice 1/4 inch bolt. And you might say, well, you know, I don't know how long the bolt should be. Well, again, bust out your evaluate tool, hit measure from that face to that face, and that's 1.25 inches. So it can't be, it's got to be longer than 1.25 inches. So let's just call it 1.5 inches. There we go. Alloy steel is always a good choice. Now they have a fully threaded or partially threaded. I'm partial to partially threaded. And hit save. Let's open that up. And there's the bolt that will hold the whole gearbox together. All the sketches hidden. They are good. So now we can simply insert these as well. I'm not going to do all of them because you've watched me do one, so that kind of gives you the feel of it here. So mate that face to that. Now, if it mates the wrong direction, which sometimes do, you can flip them here. I got it right that time, but if you run into that, that's a quick, easy fix for it. And there you go. And then, of course, you could go to McMaster. You could find the right nuts to put on the other end. But likely you'll be bolting this to a frame member, so that bolt would have to be a lot longer. So you might be putting an 80-20 or box tube, so that would be quite a bit longer. Okay, so now you have designed a gearbox to go a certain speed. Oh, that's the one thing we should do, is let's mate that. Now typically there'll be a thrust bearing in there, a little bronze bushing or something that will prevent it from rubbing the back. So I don't have that in there, but that certainly wouldn't be an issue if you had to add it. And now you'll see if you spin your motor shaft, your output. And this again is a 1:8 gear ratio. So if you were to take a wheel, which we also should have lots of in our common parts folder, let's do a Coulson wheel. That'll work. That's a good one. That's a good wheel right there. Alright, so we can mate it right to the output shaft. Now generally I mate most of the time faces to faces. It does allow things to move. If you mate a line to a line, it's much more restrictive, and then you can get the very angry over-defined. Okay, so there you go. You have a gearbox. Now you can see we have some issues because that wheel won't touch the ground. So things would have to happen, like we could move these holes down. It doesn't necessarily have to be in line. We could also trim the gearbox shape a little bit to make that work, or we could use a larger wheel. But pretty simple tutorial on how to design a gearbox, figure out what size you need of parts, figure out where to get the parts from, figure out fasteners, and how to get it all together. The great thing about this is if you do all your fasteners like this, you can go to make drawing from an assembly, and you can take your drawing, your assembly, and you can put it on there, and you could say insert tables bill of materials. And if you insert your bill of materials right there, and then you usually got to format a little because it doesn't do a very good job of that, but if you put a bill of materials in, it will list all of the parts that you have on your robot. And the great thing is you can generate a list of all the parts you need to go buy. So we can go to McMaster and we can order all these parts up in one shot. We know how much it costs, we know what we need to buy, and it comes overnight. So by knowing all these parts and the quantity of them, basically we can print out an order and have it the next day or next couple days and make this gearbox very, very quickly. The other great thing is, as long as your parts are smaller than 12 by 12, they can fit in the water jet, or 12 by 24, they can fit in the laser cutter. So we could make this out of wood, we could put it all together, we could try it and see if we like it, and then make it out of the real material later, the more expensive materials. So, and the last thing I want to hit is if you go to evaluate now, and you go to mass properties, you can see that this gearbox weighs 3.43 pounds. So if we have 4 of these on the robot, we know out of the 120 pound limit, we've used 13 pounds, so a little over 10% of our weight. So just something to keep in mind. It helps us keep track of weight. Now this is a single stage gearbox, one small to one big. You can do multi-stage gearboxes, you can do all sorts of fancy stuff. So if you have any questions, give me a holler, and excited to see what you guys come up with.